Welcome everyone to today's webinar from the IPCEI ME community. Today's webinar is on Edge AI, from hardware to real-world applications. My name is Marelle Tefera. I'm program leader at ABGI and I will be moderating today's webinar. In the next slide, you can see the agenda of today. We will first start with an introduction by Thomas Barth, who is the Director of Innovation and Public Affairs at Micromind, and then move on to specific projects, outcomes, results, and interesting talks by Fabio Pavanello from CNRS, Michael Bayer from Bosch, and Teresa Vialova from Micromind as well. So we hope you're all well installed, that you have water next to you, and then I let Thomas introduce you to today's exciting topic of Edge AI. Thomas, the floor is yours.
Thank you, Marelle. Okay, welcome everybody also from my side. I think that it is a real pleasure for me to open today's session. Actually, when we in the Transformer Group started putting this webinar together, we had one clear goal ahead: to show that our IPCEI MECT ecosystem is not just about individual projects, that it's about building a connected European value chain. And I believe today's lineup delivers exactly that. On next slide, you see why are we talking about Edge AI today? Because the world of data is shifting, and is shifting really fast. Gartner estimates that 75% of all enterprise-generated data will be created and processed outside the traditional cloud, up from just 10% a few years ago. Think about what that means for our industry. The chips, the sensors, and the accelerators that we develop with these ecosystems are no longer a nice to have. They are the infrastructure that this data shift depends on. And when we talk about real-time decisions in energy grids, in autonomous mobility, or in critical security systems, these applications simply cannot tolerate cloud latency. They need local, secure, energy-efficient processing. And this is exactly where our community holds a unique competitive advantage. On next slide, I can show you that today's session is structured as a one connected journey from photons to megawatts. It starts with the sovereign hardware, next-generation photonic accelerators, and RISC-V architecture that are redefining what low power and secure computing means at the edge. Then we move to optimization. How do you take a complex neural network and make it actually run on a tiny constrained device in a real time? And finally, the question that ties it all together: why does any of this matter? Because out there in the real world, there are energy grids that need to be stabilized and solar output that needs to be predicted from sky images. You will hear how this works today in cloud and why the path toward edge deployment is the logical next step. That is the full European value chain you will see today. And finally, on my next slide, this is not just about today. What you are about to see and hear, photonic hardware, AI optimization, and the roadmap from cloud to edge, is exactly the type of cross-border value chain that the upcoming IPCEI AST, or Advanced Semiconductor Technologies, aims to scale across Europe. So think of today's webinar as a proof point. The IPCEI ecosystem delivers real synergies from chip to grid. And on that note, our first speaker will pick up right where I am leaving off, with Edge AI. With that, Marelle, I hand over back to you, and to all of you, enjoy the session.
Thank you, Thomas, for this really nice introduction and positioning today's webinar. So our first talk, diving into the more technical details, is from Fabio Pavanello from CNRS, and he will speak about NEUROPULS, the neuromorphic, energy-efficient, secure accelerators based on phase change materials, augmented silicon photonics. Fabio, floor is yours.
Thank you for the introduction. Good afternoon, everyone. I'm Fabio Pavanello, a CNRS researcher in the Chroma laboratory based in Grenoble, France. And today I'll discuss about an Horizon Europe project called NEUROPULS. In the next slide, you can see the outline of the talk. So before diving into the NEUROPULS project, I will discuss first why we need such a project and what are the current computing bottlenecks and what photonics can do for computing. I will then discuss some of our most recent results and future directions, and then we will wrap up. You can see when we talk about computing at the edge, we mean computing very close to where the data are generated. And this means a higher confidentiality, energy efficiency, and lower latency. At the same time, computing at the edge means also that we can scale better and faster because we have a more distributed nature of computing. On the other side, though, we have quite a few challenges. In particular, we don't have the resources that we have in a data center at the edge. So we need to have hardware that is lightweight, of course, but also very energy efficient. And another caveat of having a distributed approach is the fact that we have our edge nodes can be used also as entry doors for cybersecurity attacks. So it's important to develop robust security layers that can protect, for example, data, user data, model data, and so on. And current solutions that exist, for example, in the autonomous driving sector, they are just way too consuming. When we take commercial examples, we see that they consume hundreds of watts. And therefore, there is a need for better and more energy efficient approaches. We can see that when we start to look at the data and the physics of the problem, it's not really the computing operations themselves that are expensive energy-wise. But actually, it's the fetching of the data from memory that it's orders of magnitude more energy consuming. And the same holds actually also when we want to transmit this data through a link. Current solutions that large companies such as NVIDIA and Intel are considering rely on co-packaged optics, where basically data, once they are, for example, processed, they are sent over through an optical link rather than an electrical interconnect. This provides much lower energy consumption. We are talking about sub-picojoule per bit. And also, we can support very high bandwidth densities, 4 terabits per second per millimeter short line or more. But this is very important because from a company perspective, even if the company has a very sophisticated, very accurate model, but this model cannot be translated because of hardware constraints, for example, too much cooling power, too much memory bandwidth required, then this is basically useless. I'll show you here. You can see an example of an optical link that connects a memory sector, memory array, to a compute unit. And we can see that we have some electronic fetching first, then some electronic manipulation of the data in order to be then sent over through optical engines to a compute ASIC that then does the computation and then sends back for writing the results into memory. Now, while it's really important to optimize the optical link for sending data, we see that we still have a lot of memory fetching, that data fetching that happens because, for example, in machine learning models, we need a lot of weights, activations and weights to fetch constantly from memory. So this is quite a burden from an energy consumption point of view. We can see a different approach that takes advantage of co-packaged optics, but also implements a weight storage, local weight storage mechanism into a photonic core. So photonics is not anymore used only for sending data to a point or receiving them from a certain place, but also to do the computation. And in this way, by including weights locally, then we can heavily reduce the fetching of data from memory. Of course, in order to do so, we need to have platforms that are currently not existing that allows us to do to have a non-volatile state storage for photonics, but also ad hoc optimized electronic photonic interfaces to optimally communicate with these photonic cores. I've put some of the benefits of photonics for computing. Like we can see that using light, we have access to, for example, the phase of the optical field, the amplitude of the field that we can use to encode the data onto. We have access to a massive bandwidth. We are talking about more than 300 terahertz, for example, in this case, that can be leveraged for enhanced parallelism of the architectures by using approaches such as wavelength multiplexing, demultiplexing. Another advantage comes from the fact that we can implement linear transformation that are basically powerless. They don't consume any energy, and also ultra fast, because they are basically limited by time of flight through the passive circuit. In reality, we have some losses that are due to insertion losses of basic components, but these are getting lower and lower with the advances of the field. And finally, we have access to phenomena such as interference that can be proven very valuable for computing. Brings us to the neuromorphic energy efficient secure accelerators based on phase change material augmented silicon photonics project, the NEUROPULS project. This is a 8.3 million euros budget project with 15 partners from 8 different European countries. We have 2 SMEs, 1 industrial and 1 foundry. It has a duration of 5 years and started in January 2023. You can see the main objectives that we have in this project. Firstly, we want to augment the currently existing silicon photonics platforms. In particular, we want to introduce what I mentioned before regarding weight storage by integrating in the platform phase change materials. And on the other side, on the right side, you can see 3-5 materials that are integrated onto silicon for gain purposes, for example, developing spiking lasers. Based on this platform, we are developing a series of devices and architectures that leverage this technology while being ultra energy efficient. And as I mentioned before, we need security layers that are robust. We are developing hardware security primitives using the very same technology of the photonic accelerator. And these primitives are leveraged then by protocols that take advantage of their benefits. Interfaces are an important part of the overall effort, and here we are developing open source based RISC-V interfaces that are optimally addressed for driving the photonic accelerator. And finally, when we are looking at the overall system, we want to simulate not only the photonics but also the electronics and how the driving core, the RISC-V driving core, interfaces with the photonics, and therefore developing a Gen 5 based simulation platforms that allows to do that. Finally, we want to showcase our prototypes that are currently fabricated by CLETI for fields such as autonomous driving and cybersecurity. You can see some of the qualities that the phase change material candidates need to have in order to be optimally useful for photonic applications. Phase change materials are materials that have 2 separate phases, very stable, crystalline and amorphous, and these phases can be triggered very rapidly, nanosecond scale. They can be actuated by optical or electrical pulses, by local heating, raising the temperature locally of the phase change material. And the interesting characteristic is that these materials, they have a very strong change in their optical and electrical properties once switched. We can see that we've investigated various compounds of phase change materials, particularly for photonic neural networks. And in this case, we want to have a non-negligible change in the real part of the refractive index, the numerator that you can see in this figure of merit, while introducing as low losses as possible, because we are basically integrating, we are embedding the optical weights in these changes of refractive index, but we don't want to suffer the losses that come with that. When we propagate our signal through our computing core, we don't want to lose all the optical signal. We want to keep a very large signal to noise ratio. And we've seen that the germanium selenide is particularly interesting because it has very low losses, both in crystalline and amorphous phases, which is ideal, but a non-negligible refractive index delta N. You can see an example of how we are leveraging this phase change material in the platform, specifically germanium selenide. You can see it sandwiched on the left side in the cross section, and placed above the silicon waveguide, the strip silicon waveguide. And by basically changing a classical uniform rectilinear heater that drives, raises the temperature and introduces the switching, the encoding of the optical weights, by changing it to a segmented architecture, we can see that it's possible not only to have at maximum 0.3 dB of insertion loss, which is pretty low, but of course, the lower, the better. But also we can increase by almost a factor of 5 the number of levels, of encoding levels, if you want, the resolution that we can achieve with reasonable driving conditions, for example, using pulse width modulation. We've been using these building blocks to develop more advanced architectures, photonic computing architectures. Here you can see an example of a recently published one. We called it a braid architecture. It's a very symmetrical architecture that allows us to do linear transformation in the complex plane. And what is interesting about this architecture is that thanks to its symmetry, it allows us to be better able to map matrices. You can see that when we look at a classical matrix, the fidelity, which tells us how well we are mapping a given matrix to a target one. We basically, in taking into account the insertion loss of, in this case, of a beam splitter, how much loss is lost is introduced when we pass through a beam splitter, or its imbalance, so how much the two arms are in balance between each other. We can see that the braid architectures performs better than more classical and widely used architectures in literature. And this is very important when we want to build robust and reliable photonic neural networks. We take one step above, and we look at how now we can use the photonic core, this braid architecture that we developed, in the full pipeline of AI. So we are taking basically an AI model that is pre-trained. Then we look at and select what modules are required and wait for mapping them to our hardware. Then we do an hardware-aware representation of these modules in order to have them fitting better to our hardware, to our architecture. For example, we can also have a folding in time of the models. And then we translate this into basically matrix vector multiplications. And finally, we take this and we map them onto the actual braid architecture, our hardware, and doing it either analytically or numerically through backpropagation. And doing so allows us to have an end-to-end inference for a model where we take into account our photonic infrastructure, our photonic hardware. Moving one level higher, you can see that this is the framework of our Gen 5 platform, simulation platform. And you can see here that now we are not only focusing on photonics, but we are also focusing on how the photonic accelerator interacts with the driving RISC-V core. And in particular, this framework is useful for design space exploration because we can implement multiple domain-specific accelerators that then we can benchmark according to metrics, for example, such as power consumption, latency, when fault ratios, when we take into account how actually in a realistic scenario, how the accelerator is driven by our core, RISC-V core, for example. In future, we are aiming to benchmark our simulation platforms with actual experimental data that will be obtained by our prototypes, packaged prototypes that are currently being fabricated. To wrap up, I've discussed about how silicon photonics platforms that are particularly well suited for co-packaged optics can be enhanced, for example, by introducing non-volatile phase change materials to have them better suited for computing applications. I've discussed how architectures, how important metrics such as insertion losses, robustness, tunability, energy efficiency are important in architectures when we are looking at how they scale with dimensions. And finally, I've discussed about how these systems could be modeled at a very high level by leveraging Gen 5 simulation platforms for optimal electronic photonic co-design of the next generation of computing accelerators. I would like to thank you all, and if you're interested to know more about our project, here there are a few links.
Thank you, Fabio. Of course, the audience is free to ask questions in the dedicated Q&A section of this webinar or in the chat. It was very interesting to hear there's more like fundamental research related questions and the project you have ongoing. So thank you very much for that again. We are now moving one step ahead to hardware applications and the neural architecture which is used for that, presented by Michael Beyer from BOS Research. So Michael, the floor is yours.
Thank you very much for the introduction. So in the IPCEI program, we are located in the Think workstream, and we let Bosch work on future E architectures as well as next generation vehicle computers. But for today's talk, I want to focus on hardware-aware AI perception inference optimization, specifically for automotive compute devices. Before we dive into the technical details, though, let's first take a look at why inference optimization is crucial for embedded deployment. Generally, in today's embedded AI landscape, next slide, please, we have three trends that influence each other as well. So the first one is from the application side. So we have different applications ranging from ADAS systems, AI cockpit functionality, robotics, and drones. And each of those come with different compute requirements and possibly also different target platforms where they should be deployed. Secondly, we also have different technology trends, both on software and hardware side. So there's emerging memory technology and the current general availability of memory and its cost and price situation, basically, but also the software-defined vehicle as well as chiplet-based systems are gaining more and more traction and become more and more important. The third point here, the third trend is the neural network architecture itself. So those are evolving rapidly in the last few years. Not too long ago, basically, CNNs, or convolutional neural networks, were predominantly used. But nowadays, we mainly talk about transformers, LLMs, VLAs, VLMs, and the like, and whatever the future holds, basically. What they all have in common, though, is that each of these network architectures, we require good hardware utilization to deploy this to an edge device. And these trends are just a part of what makes it really so challenging to deploy neural networks on embedded devices. Next slide, please. Because typically other factors also come into play that we want to consider. So for instance, the cost. We want to get the best AI performance per dollar we spend. We want to think about efficiency and power consumption, so maximizing the throughput on a given hardware architecture for a given neural network, or depending on the use case, also focus on energy efficiency. Lastly, also flexibility plays a crucial role because we need to adapt to different challenges that arise, and also we want to gain time to market, basically. Overall, next slide, this paints a clear picture that there is a need to adapt to diverse trends rather frequently, but also in an efficient and fast manner. Next slide, please. And this is ultimately why we developed the Bosch AI inference optimization toolchain. Typically, next slide, you start with a basic neural network architecture that is trained on some data set and some task. And our optimizations here, next slide, focus on three main pillars. And the first one is hardware-aware neural architecture search. The second one is hardware-aware quantization and sparsification. And finally, we have hardware-aware deployment optimizations. Next slide. Our optimization is built upon the vendor toolchain then. So after we optimize the model, we deploy the model using the vendor toolchain to different hardware targets, depending on the use case, as well as the requirements of the specific application, basically. In the following, I will then go through these individual steps, and we start with neural architecture search. What is neural architecture search? So basically, we have a set of experts and a reference model from which we start, and some task data where the model has been trained on. And then we have some hardware metrics that we want to consider in our optimization. So this could be, for instance, the latency of the model running on a specific hardware device. We then define a search space for a given network architecture, and this ultimately could mean something like the number of layers the network has, the types of layers the network has, activation functions, the interconnectedness between different layers. And this is the expert input that is then fed into our hardware-aware neural architecture search framework. Next slide. This is a fully automated tool that then uses these three inputs that we've defined earlier to come up with a set of Pareto optimal architectures. Next slide, please. So using these three inputs, we then optimize the network architecture, basically, which we will get to in a second. And the output then looks something like this, what we see here on the right-hand side. So here on the y-axis, for instance, this is the accuracy of the network on a specific task. And on the y-axis, on the x-axis, we would then have a hardware-specific metric, such as the latency of that specific network architecture on the hardware. And since this is a Pareto-optimal set of network architectures then here, we can then select a optimal candidate based on our application's requirements. So this could be either a latency constraint or a specific accuracy constraint that we have to reach. Next slide, please. One way to do this is two-stage neural architecture search, and this is what we will take a look at in the following. Basically, the idea is to make the dimensions of the model, so the number of layers, the activations functions, how they are connected, elastic during training, and then search for an optimal architecture. This is a so-called one-shot model. So we have a big supermodel, and from this one, next slide, we would extract different network architectures, which then have a good performance, basically. Next slide. This is a two-stage approach. So this one-shot model, we would basically train just once, and this is the expensive part here. And then afterwards, in the second stage, we can then search for these Pareto optimal architectures. So from this one-shot model, we then generate a neural network architecture. We extract a submodel. This is really cheap because it doesn't involve any kind of training. And these submodels, we can then in turn evaluate on a specific test data set. So we get an accuracy number as well as a hardware number because we have hardware in the loop capability. So at the end of the day, each of these hardware architectures, network architectures, we can optimize for both accuracy and hardware-specific metrics. Once we've satisfied with our optimization loop, so if we've reached the latency goal, for instance, we can then continue with the next part of the optimization toolchain, which is compression. Next slide, please. What is compression, or what is quantization in a nutshell? So typically when we train a neural network, it's trained in a floating point data format. So here on the left-hand side, we see a 32-bit floating point number, for example. And then quantization is then the process of converting a floating point number to a fixed point integer number. So this could be 16, 8, or 4 bits. Next slide. And the benefit here for embedded deployment is basically that, of course, we decrease the memory footprint of the model. So rather than storing 32-bit for a floating point number, just storing 8-bit for a weight, for instance, just significantly decreases the memory requirements we have. But also taking the number of operations we have to execute for the same number of bits. So for one floating point 32 operation, basically, if we have the hardware support for this, we could also squeeze in 4 integer 8 operations, basically. So this in turn increases then the inference speed of the entire model. But as Fabio already pointed out in his talk, also energy efficiency plays a crucial role. And since data movement from external memory to the accelerator chip itself is the main contributor to the energy consumption of the whole system for neural network inference, just decreasing the number of bits we have to transfer through quantizing the model increases the energy efficiency of the entire system. The last point here, task performance. This is something that is model dependent and task specific, I would also say, but we will take a look at this in a second. Next slide, please. So to sum this up, why we do quantization in the first place, basically it enables us memory and runtime benefits, and specifically for deployment on edge devices, it's just a major step that we want to take to benefit from these improvements. Next slide. So PTQ, post-training quantization, is what's typically done after you train a model, and then you quantize this using typically a set of representative calibration data. But it's not guaranteed to maintain the model task performance. So specifically for more advanced tasks, such as 3D object detection, it can happen that the model performance after quantization drops quite significantly. Next slide. And what we do here is, with our Bosch compression framework, basically we have one of the tools is quantization-aware training. And this models the effect that quantization has during deployment on the edge device, already during training of the model. So at the end of the day, the goal is basically to simulate the effects that quantization has, so the errors it involves, and then fine-tune the model such that it can recover the loss in task performance. It's shown here on the right-hand side how this typically looks. So we have a framework that can easily be integrated into existing deep learning frameworks, such as PyTorch. We just take the model, some configuration as well as the data sets, and then we include some optimization functions such as hardware-aware pruning, sparsification, as well as mixed precision quantization. And mixed precision quantization here is specifically interesting because depending on the task, we might not want to quantize the entire model for a specific bit width or to a specific bit width, but we want to have a more optimal trade-off between compression of the model task performance, the model latency on the specific hardware targets. And this is where mixed precision really comes into play. After these optimization methods, we then obtain a compressed model and maybe some quantization overrides. Next slide, please. And then we complement or even extend an existing vendor toolchain features. So this optimized model and the data set is then fed into the vendor toolchain, which then ultimately generates the final binary that is executed on the target hardware. Next slide. So now we have an optimized hardware architecture as well as a quantized and compressed hardware network architecture. And the final step that we want to do now is optimize the deployment itself. So here on the right-hand side, we see a symbolic execution trace of a neural network on a specific hardware architecture. And each of these bubbles then is basically the time for a specific operation on the specific hardware architecture. Right off the start, we can see that there is a huge bottleneck in there. And this basically stalls the entire inference for a given period of time, which is not ideal when we want to optimize for latency of the model. What we can do here is optimize the deployment of the model on the graph architecture level. So a simple example here, we implement a mathematically equivalent modification of the computational graph. So if we want to compute the sum of a squared b squareds, this is mathematically equivalent to a times a plus b times b. Pretty simple. But here on the right-hand side, we basically see how we transform the graph to a similar representation on the right-hand side. This is, of course, a hardware-dependent optimization, but next slide. What's really great about this is that we immediately can see that the latency of the inference bottleneck is basically gone, or at least reduced. So we benefit from improved runtime, and it's without a loss in task performance because it is a mathematically equivalent transformation. Using all these three optimization methods, so we have an optimized model, we quantize it and compress it, and we optimize the deployment for the network on the hardware architecture. We can now take a look at the actual result that we achieved. The use case that I brought here is a multi-view perception. So here on the left-hand side, we see that it's a network that takes 6 camera images as inputs and then produces 3D bounding boxes in 3D space of objects surrounding the vehicle. So on the bottom here left, we see what a bounding box basically is. It is a height, length, and width and orientation of a bounding box in 3D space. And each of these bounding boxes also has a class associated with it. So is it a vehicle? Is it a pedestrian, etc. On the top right, this is an abstract overview over the network in question. So this is an open source variant of the former Tiny. And as I said, it takes basically these images as inputs and produces these bounding boxes. What we show here is a comparison between just using the vendor toolchain and using the vendor toolchain plus our optimizations. And here, for this specific model, we see an inference speedup of a factor of 5.4x, which, next slide, is pretty great because if you think about embedded edge AI, we can really show that hardware-aware optimizations, as we do it, enable the deployment of these state-of-the-art vision models on such embedded compute platforms. And in turn, this also allows us to better utilize the compute resources, which is critical for edge AI applications. Thank you so much. This is all from me for today, and I'm looking forward to your questions later on.
Thank you very much, Michael, for this interesting talk about the hardware applications. So, of course, besides the hardware applications, there are other use cases to take into consideration and more practical applications. So with that, I would like to hand the floor to Teresia Fialova, who is data scientist at Micromind. So Teresia, the floor is all yours.
Yeah, thank you very much. Today I would like to talk a bit about how edge AI application can look in practice, and specifically about solar power nowcasting that we do at Micromind. The next slide, please. Okay, so today I will cover first a short motivation to why solar power forecasting is important and what are common approaches to do it. Then I will dive more into how we do it at Micromind and how our forecasting model works. And finally, I will have a few words about our model deployment and our plans on edge deployment specifically. So we can move to the next slide, please. Okay, so very shortly, something about me. Yeah, I work as a data scientist at Micromind, where I work at this solar power forecasting project, which I will talk about today. And I focus on deep learning and computer vision specifically. And the Micromind company is a company that focuses on energy intelligence and is direct APK partner. And we participate in work streams Sense and Think. So now let's move to a short motivation. Thank you. Next slide. Yeah, so if you own a power plant and you want to distribute energy that you produce, you obviously need to use power grids to distribute your energy. However, these power grids are designed for stable energy sources and they require to be at balanced state at all times, which is quite a big problem for energy sources that are very variable in production, which is solar power plant case. So since we have variable production, or the owners of the power plants, they are required to trade their energy in advance in 50-minute long windows. So they have to tell in advance how much energy will they deliver and produce. And if they under or overproduce in comparison to what they traded, they suffer quite significant financial losses. So that's why we focus on power prediction or forecasting, and that's why it has value to those owners. On the graph on the slide, you can also see an example of how variable solar power production is throughout the day. So we have 1 day production plotted on the graph and different time window aggregations. We can see that in 1 minute aggregation time, the variability is really large. But what is interesting to us is that even if we take the 15-minute long trading windows, that's the blue color graph, the variability is still quite significant. Okay, so we can move to the next slide. So that's why power production forecasting matters, and it's really valuable. Common approaches are satellite or top-down approach and then ground-based approach. Satellite approach uses satellite data as a main input to forecasting model and has advantage of large-scale coverage. So we can see quite distant clouds. We see mostly everything that can have an effect on how much the sun will shine in future, and in turn how much solar power energy we will produce. However, the disadvantage is low resolution of the data and quite infrequent updates, which also means infrequent forecast updates. On the other hand, we have this ground-based approach, which is the approach that we chose in MicroMind, where we capture the sky and the cloud information from the ground. So we have a camera installed which captures the sky. And this way we have very high resolution data and also high update frequency compared to the satellite data. And also another advantage is that since we are already deployed at the site and we are collecting information, we can also collect other site-specific information such as current, solar power output, or for example, temperature or wind speed. Next slide. And next slide. Now I want to talk a bit more how we approach this problem and how our forecasting model works. So first, as I already said, we use sky images to forecast future power production, and specifically we decided to focus on nowcasting, which means a very short-term forecasting which spans up to a few hours. Specifically, we do 50-minute forecast ahead in 5-minute intervals, and we chose this short-term forecasting because we think this is the space where we can benefit the most from the high resolution and high update frequency of the sky images. You can see on the slide an example of input image sequence that is the main or the base data source for our predictions that we capture with our ground installed cameras. In the next slide, I want to talk a bit more about our data collection. So we have a custom hardware for data collection installed at each photovoltaic site where we provide forecasting. We collect data in 10-second frequency, and we collect sky images with an installed camera, sun irradiance with a sensor, also meteorological data, and also we monitor and collect the actual solar power output. We can move to the next slide. So we have all of this data collected, and now we need just the forecasting model. So our approach to forecasting is actually a two-step pipeline where we have two models. The first model takes all of the past observation, that is a sequence of past sky images, metadata, and sun irradiance, and we forecast using this old data, we forecast future irradiance. So we actually first do sun irradiance forecast, and then we take this forecasted irradiance and we use a second model, conversion model, which just transforms the irradiance to actual solar power plant output. And this is our final forecast, like individual power values that will happen in future. Why we decided to split this forecasting process into 2 steps is because we want to deploy to multiple sites. And actually, this first step can be shared across all of the sites, because the sun irradiance is independent of a specific photovoltaics installation. So we can have this strong forecasting model that we train on all of the data that we have from multiple sites. We can share it across sites, and then the site-specific model is just a conversion model, which is very lightweight, and we train it for each site specifically. And this model accounts for site-specific information such as panel angle or panel efficiency and similar information. You can move to the next slide. Now I'd like to talk a bit about the deployment of our model and why we want to move our deployment to edge. So our current state is that we have live inference operational. So that means we are already providing forecast in real time for a specific photovoltaic site, but we are still run on cloud. And we, in the next step, would like to move this inference and running the model to the edge device that will be located on each photovoltaic site. We have a couple of reasons for this. They are like maybe typical reasons that you hear in context of edge, but they really matter to us. First of all, it's data privacy. If we run inference on edge, we can guarantee data privacy for customers for which it is important. Other reason is offline capability, or like being able to provide inference and forecasting offline. This is mainly for 2 reasons. The first is that photovoltaics installations can be located in remote areas, for example, some mountainous areas where you have no internet coverage. And the second reason is that, again, some customers prefer to keep their devices offline for security reasons. So this way we can provide both of these use cases. And finally, deploying to edge can also provide lower latency, since we don't have to send data for inference over the network. And since we use image sequences as an input to the inference, this data is not so small. Okay, we can move to the next slide. So currently we are in a stage of hardware selection, where we have a few requirements on what do we want from our hardware. Let me just quickly summarize through them. So as I already mentioned, the latency, we want the hardware to have low inference latency. Specifically, we would like the latency to be lower than our incoming data frequency, which is now 10 seconds. Also, we would like to be able to do overnight training. This is something that may be not like required always, but we want to have this option to always at night retrain or fine-tune our model on the last day data, so that the model is always updated. And this is again important in cases where we have deployment at sites where there is no internet connection, for example, and it's quite hard to update the model remotely. Or in case where we are deploying to a new site where we don't have many data yet collected, so we want to gradually update the model as we collect more data. Another requirement that we would like to have is that the hardware would have reasonable or affordable cost, since we're also targeting smaller producers, so not just large companies, and we're trying to keep like the cost of the full installation in reasonable amounts. So to help us with the hardware selection, we collaborated with university, which did research for us, and they benchmarked and tested different selected hardware using our model design. And we have now some results from them. They measured inference time, training time, and also gave us a lot of notes on which model or model adjustments and which hardware are compatible, what are some maybe problems we have to look at, and we will now evaluate those results and choose the hardware that will be like most aligned with our requirements and needs. We can move to the next slide. As I mentioned, there are a few options suggested from the research that we could do if we had problem, for example, with small memory or too long time, computational time or latency. One of the suggestions was, for example, switching from LSTM unit to GRU unit. I didn't mention, but our model is based on conv LSTM units. So GRU unit is similar, but with fewer parameters. And this is, for example, one option we could try, or decreasing input images, but both of these options decrease the performance of the model a bit. So these are just options we will maybe look into if we will have some problems with the hardware that we will choose. Okay, we can move to the next slide. So just to sum up, our next steps, as I said, are selecting and finalizing the hardware selection and continue on or move our deployment from cloud to edge. And then we also work still on deploying data collection and inference to new sites. And we continue on improving our forecasting model. That's all from me. I hope I showed you an example of how a practical application may look like and why the edge is important, like from the perspective of a practical application.
Many thanks, Theresia. I think there are some exciting times ahead with those next steps and experiments to be done. So staying within MicroMind, Thomas, I'll let you wrap up today's session before diving into the Q&A.
Thank you, Mirel. Thank you. And thank you to all three speakers also from my side. Okay, what you have just seen is not something that happens by accident. I think that it's quite clear that it is a result of our ecosystem. We went from the physics of light in a chip through the mathematics of model optimization all the way to a real energy grid that needs to be stabilized. That is the European value chain in action. We opened this webinar with a question, why HI and why now? I hope that these three presentations gave you a concrete answer. And with the IPCEI AST on the horizon, I hope that this is only the beginning. I'm now very curious of the question. Mirel, over to you.
Thank you, Thomas. So indeed, very interesting talks. Thanks to all the speakers for having put this together, explain to us what you're currently doing, what are the next steps, and what can we expect. So we have some questions from the audience as well. And of course, if other questions come up, please don't hesitate to put them in the chat or in the dedicated Q&A section. The first question is addressed to you, Michael. What is actually the benefit of supporting multiple hardware targets?
Yeah, thanks. So I think flexibility here plays a role. So if we optimize for different models, for different hardware architectures, depending on the use case, it might also be more efficient for a specific network architecture to be deployed to a specific hardware architecture. And this is mainly one of the reasons why we do it, I would say. The other one is also that generally being able, from an optimization point of view, having the flexibility to optimize to a different hardware architecture, it's quite a big plus. And if you take a look at this question from maybe a supply chain point of view, also there having the flexibility to adapt to a market situations, maybe it can improve the delivery of results to a customer, for instance, so from a company perspective. And we try to tackle this with our methods that are hardware aware. So basically using our optimization toolchains, we can tailor specific optimizations to a given hardware target and the given neural network architecture.
So actually, there's many benefits in having these multiple hardware targets. So thank you very much for explaining this to us. Not so much about having multiple targets, but more about upscaling. Fabio, there is a question on whether or not photonic computing could scale beyond just demos.
Well, this is an interesting question. Thank you. It's not straightforward indeed at first, less because photonic devices have a much larger footprint than transistors, than electronic devices. However, there are quite a few techniques that can be used. I talked about parallelism, for example, so exploiting different degrees of freedom that are not existent. For example, in digital electronics, to scale. We are looking in particular during the presentation, I discussed about this pipeline that can allow us to map AI model onto our photonic hardware. Here we are envisioning to have different tiles that work in parallel, and each tile contains one of the photonic cores that I've shown previously. And by doing so, and take full advantage of the platform that we have, we can actually scale to reasonable use cases, reasonable dimensions. This is especially well suited, I would say, at first for edge computing, which doesn't necessarily require the same model sizes that are instead available and required, for example, at a data center level.
Okay, thank you very much. So I think a step-by-step approach is the best approach here, but the future is very bright to play a bit with the words. We have another question again for you, Michael. Have you tested for neural network partitioning techniques across heterogeneous accelerators? And what do you think about its potential in enhancing the inference performance of edge AI?
Yes, thanks again. We are aware of this heterogeneous compute and deploying to different accelerators, specifically considering chiplet systems. This is definitely a topic that we are investigating right now. Specifically from a potential perspective in automotive devices, I think there is also, beyond looking just enhancing the inference performance, there are also some safety implications that we in our group here want to take a look at as well. So definitely on our roadmap, but nothing that I can share here at this moment.
So exciting times ahead. Let's get in touch again in a year to hopefully have a bit more results on that. And then to finalize today's session, Theresia, there's also one question for you on the sky camera, which might give much more detail about cloud movement compared to a satellite view. However, isn't it a limitation that you can't observe more distant clouds, even for the 50-minute forecast horizon you mentioned?
Yeah, thank you. So this is something we are aware of, and actually we are planning on to evaluate the last few steps of our 50-minute prediction in terms of if our prediction is if we should still rely on the sky images or if we should outsource this prediction to satellite-based prediction, because we also work on prediction up to multiple hours where we already are using satellite-based irradiance prediction. So now it's just like for us the question where to make the change or how to overlay this to kinds of prediction so that we get the best prediction overall.
Okay, thank you very much for your answer. And with that, we are exactly in time to finish today's webinar, but of course not without thanking all of you for your very interesting talk. Thank you to the audience for watching this webinar. A replay will be available soon. And of course, stay informed about the IPCEI MECT activities and maybe meet our speakers and other partners in the network in our next networking event, the IPCEI MECT Connect event in Dresden in June. So thanks again to all of you, to the speakers, to the audience for having taken time to discuss Edge AI, and looking forward to what the future will bring. Thanks again and have a good afternoon.